I'll play the race car all day.
Oh, man.
All right, what we going to talk about are sensors here. Everybody got your pencil and your paper and all that, huh? Pencil, paper, cell phones put away, all that. No text messages coming or going.
Brandon, I
Turn off
can't help
the
it
ringers.
come in now.
I say that, sometimes I
Can't
ring
help
on
it
my cell phone.
going out.
Yeah,
Uh-oh. What?
PM sensors measure the speed and position of rotating parts. PM sensors.
This automatic transmission?
What's a automatic transmission test 6? What is a PM sensor?
Sensor.
How's about pull up?
Huh?
How's about pull up?
Okay.
This is a PM sensor right here. See that rotating part with all those teeth on it?
Yeah.
See, I got an old motor hooked to that. Rotating part, permanent magnet. This is a permanent magnet sensor. It's got wire wrapped around there. And the signal that comes out of there is going to be shaped by the spacing of these teeth and the speed of that thing. So that's a permanent magnet sensor. I'm going to have to use that board up there, and I'm going to see if I can cram every one of my ignition parts on that so that I can use that for an ignition demonstration board. Yeah, Gene built those for me up there. But I just thought about that as I was holding that. Anyway, the resistance of everybody understands PM sensors, right? You understand how a PM sensor works? I need to make sure everybody understands that.
Like a magnet.
You got a magnet. And you're going to...
It's on the handout.
And I'm just giving you a little bit.
It's on the handout.
See that? I'm wrapping wire around this. Well, you got to wrap more wire than this, but this is just basically giving you got that? All right. Now then, we're going to have a wheel with teeth like that going by. Got that? Everybody understand that? Now the gap in between here is pretty important, because if the gap is not close enough, your voltage won't be high enough. Now in some cases, we'll have a sensor that looks like that, but it will actually be a Hall effect sensor, and on those, the spacing between here and here is critical. These permanent magnet sensors, and Delphi is one of the companies that makes them. And I pulled a little product sheet on the Delphi variable reluctance, is what they call these, variable reluctance sensors. They call them permanent magnet sensors in your book, but a variable reluctance is the one that I just showed you on that board. Is from a Ford, they call it variable reluctance. Anyway, the VR sensors that Delphi makes can put out from like 0.25 to 400 volts. 400 volts they can put out. And that's something that knock the snot out of you. All right. So anyway, this magnet, the way that this creates is, see, your computer is actually reading right here. The computer's reading up there, and I need to make sure that I got my camera angle where people can see my drawing if they happen to be watching the video, right? Yeah. Well, he better be. That's all I got to say. All right. See that? Variable reluctance sensor. Now, every time this metal, it's got to be ferrous metal. What's ferrous metal? If I say ferrous metal, what am I talking about? What's the elemental symbol for iron? Fe, right? So iron or steel, something in a magnet. If this was made out of copper, you wouldn't get no signal. If it was made out of aluminum, you're not going to get no signal. That's why some of these movies you see this people picking up, doing something with a magnetism that's moving something that's made out of aluminum. I'm sorry, X-Men, that don't work. You know what I'm saying? All right, so right here, if you move this thing back and forth, the magnetic field is going to be running right here. And when you move it to a place where there's a gap, the magnetic field shifts over here. So as this magnetic field shifts back and forth, what you're getting up in here is this right here. That's how that works. You got that? Everybody understand that? All right? I just got to draw my pictures better. That's what I got to do. All right, there you go. So there you go. That's how a permanent magnet sensor works. If I don't tell you that, I'll forget it. Okay. The resistance of a PTC thermistor increases as the temperature it monitors decreases.
What are we going over?
Automatic transmission test 6.
Okay.
Automatic. What, you got the wrong test?
Yeah, we have manual transmission.
That's tomorrow.
It's West Fall.
The resistance of a PTC thermistor increases as the temperature it monitors decreases. Is that right?
That's it.
The resistance of a PTC thermistor increases as the temperature it monitors decreases. Now, what is PTC? Somebody tell me what PTC is. Come on, guys, don't you read the book? What's the matter with y'all? All right. What does PTC stand for? You find that in your book somewhere, Lawrence? Let me ask you this. Here's the way I remember that. If I've got spark plug wire, or any other kind of piece of wire, or a winding or something I'm checking the temperature, I'm checking the resistance of. If I've got my meter hooked to it and I'm measuring ohms, and I heat this thing up, whatever it is, the ohms are going to go up. It's going to get more resistance. That is positive temperature coefficient. And I despise this telephone. Let's put it out there. Hello? Hey. Yeah, I'm going to do it all day. All right. Appreciate it. All right. Got Mid Shirley bringing our parts. Always Enterprise. They did something?
It's false. Number 2 false.
Huh?
Number 2 false.
Okay, so if the resistance of a positive temperature coefficient thermistor increases as the temperature decreases, that's backwards, isn't it?
Yep.
What do you call that?
Says it increases. That's the same way your temperature supposed to work, right?
Negative.
What's this one? I don't know.
Negative temperature coefficient is what they're describing.
Alright.
If you decrease the temperature, the resistance increases. That's what your sensor on your, you know one of those in here? Somewhere. Your engine coolant temperature sensor, your air intake air temperature sensor. Like if you take a meter and you take an intake air temperature sensor off of a car and hook your meter up to it, you can blow on that sensor and it'll change the temperature by going, actually the cooler it gets, the lower the resistance gets. And if you run a little heat across it, resistance goes down. So it gets less. And what does that do, though? Let me ask you this. A negative temperature coefficient sensor, I've got my PCM here. Am I running this pretty good? And coming out of my PCM, I got 5 volts. And over here, I got ground, which Ford likes to call that signal return. And I'm going through this sensor right here. All right, and it's got a resistor element in it. Okay, now I've got this screwed into an airstream of some kind, or maybe coolant, or anything I'm wanting to do. All right, so we're measuring, there's actually another resistor in here, so we're actually seeing, if we measured this right here, right there where it goes to the PD, we measured 4.6. Okay, now, as this thing starts out really, really cold, 4.6 is minus 40. All right, now let's see who can remember this. Tyler probably remember it because he's pretty good at remembering stuff. If I was going to say something was 40 degrees below 0 Celsius, what would that be in Fahrenheit? Same thing, because that's where they cross, right? So minus 40 is what, if you unplug that sensor, minus 40 is what that means. So if you see something on your global OBD2 reading minus 40, and you know that it's unplugged or the wire's cut, or the sensor's open.
I'll say if the sensor goes bad, will it tell you it's minus 40?
It will if it's open. If it's shorted, it'll tell you, that it's 256 degrees or something like that. All right, so basically super hot is shorted, super cold is wide open. So, all right, as this, whatever is in here that you're measuring gets hotter, the resistance in this actually reduces and actually goes down. That's negative temperature coefficient.
Okay.
This is NTC. So the resistance goes down as it gets hotter. And that causes this voltage to be shorted away. So if this thing here is like a little over 200 degrees, let's say if you're measuring water, you're going to be reading about 0.6.
Okay, I get you.
All right. Now what I used to do on these Ford Tauruses when I wanted to see if the fan was going to work, I would unplug this, and I would put me a little potentiometer in there of my own, purchasing and everything. In other words, I put me a potentiometer in here, And this one of the things I bought from Radio Shack, and I would make sure it was like a 0 to 50,000 ohm or something like that. And then I would take this right here and hook it there, and then hook it right there. Don't even hook up the third one. And I could watch that voltage with my meter or the scan tool even, while I turn that knob, and I could dial that thing down to the place where the fan was supposed to come on.
Huh.
Even the engine would be bone cold. Now on the old mobile out here, the motor's got to be running before it'll turn the fan on. It won't turn on the fan. If you just got the key on, you may read a voltage where the fan should come on, but in its logic, it's that if the engine ain't running, this thing ain't getting hot enough where it needs a fan, so I ain't turning it on. 0.45, 0.45, which is 450 millivolts on the Taurus is where the fan kicks on. I didn't even have that in a book nowhere. I just discovered it experimenting. And so that's how I get to where I was checking the fan. You see what I'm saying?
You got what, like some kind of knob on it where you can change the ohms?
Yeah, that's actually a little what we're talking about is something that looks like, and you can buy these at Radio Shack, something that looks just like that. Now this one right here is 0 to 200 ohms, and it'll tell you on the back of it. This one won't work for that. You better have like 0 to 50,000 because you're going to have thousands of ohms on these sensors. It's not going to be like, say that's 0 to 200 there. Now think about this. With that one there, you could check a fuel gauge. Think about it. Hook a son of a gun up between the ground and the fuel gauge, and you dial that thing, switch a key off and on so it'll correct quickly. You can get your fuel gauge reading. If you dial it, like if it says in your book, it says, 11 ohms is empty, 145 ohms is full. You can go between, halfway between 11 and 145, and you've got half tank. So if you're checking your fuel gauge, you unplug it, and it goes to full. Short it together, it goes to empty, hook your little thing in there, and you can dial it wherever you want it to go. Remember, though, because of your slosh module circuitry, you're going to have to switch a key off and back on for it to correct quickly. I don't know if you've ever gassed one up with the dadgum engine running. You're not supposed to do that, but if you do, a lot of times the silly gauge is moving so slow. Give me that, Nick. The thing is moving so doggone slow. You might be confused if you just try to dial this to a reading and look for it to change while you're dialing. Ain't happening. Because they don't want the gas doing this while you're sloshing around corners. Now in your old 70s model cars, a lot of them would, you take off, in your old 72 model 442 Cutlass,
Yeah.
you know what I'm saying? You could take off on that thing and it would go click and it would hit the bottom, then it would come back up not quite as far as it was before. Because you used some gas. All right. Now, I don't know how I got off on that, but one way or another.
Can you use one of those to turn on a fan?
You can. You definitely can. You ain't gonna run the fan through it. You're gonna tell the computer what you want it to see.
No, I'm talking about not using a computer.
No, you can't do that. You're gonna have to have something to carry the load of that fan. You're gonna have to have something that's smart enough to recognize what you're doing there. If you run the fan right through that, it's gonna cook it.
Okay.
Now you can use a rheostat, a really good quality rheostat to turn on a fan and make it go any speed you want it to. And it's designed to carry current. It'll have a ceramic resistor, that's made so that you got a contact sliding on that little thing. You see like on your headlight switch, you got that little spring-looking thing that the contact slides on. It's got a ceramic resistor, something like that, except a little better quality would operate a fan. Because fans, pull, 30 amps or something.
Can you get it from Radio Shack?
Not a rheostat. If you get a rheostat from Radio Shack, I'd be surprised. You just get one in from somewhere else. Radio Shack's got potentiometers and stuff, and they got, wussy little electronic stuff. They ain't got no big, heavy-duty stud stuff like you need for what you want to do.
Can't you test the fan? Hooking the meter up to it and spinning it like you did.
Or hook a light up in series.
Mm-hmm.
Ground on one side, test light on the other side, hook to power, and if you turn it through, if the light winks off. But you want to know if the computer knows enough to turn the fan on.
Mm-hmm.
See what I'm saying? I'm not actually checking the fan. Let's say I know I got a good fan, but sometimes it ain't working.
Yeah.
Then can the computer even turn it on? Well, you can warm the darn thing up until it's at 240 degrees. Say, well, it ain't coming on. Now the motor's hot, so what am I going to do about that? Or you can go ahead and when the engine's still cold, but know what your criteria is and dial it in and watch it on your scan tool, let it kick the fan on so you know.
That's what some people talking about.
Yeah, okay. But anyway, number 2 is actually false because the positive temperature coefficient thermistor goes the other way. It actually increases resistance as the temperature increases. Number 3, a throttle position sensor is a potentiometer. This thing I just showed you is a potentiometer. The thing I just showed you is a potentiometer. And it's basically, you know, the way it looks is it's got a wiper. You know, we've talked about this in here before. And it's got a, you know, this wrap right here. This wiper right here moves up and down. That's where you change. This right here is going to ground. This right here is going to power. All three of them are going to the computer. And as this moves up and down, this is going to change, and that's going to give you the position. So it's an analog reading, though. You know what I mean? It's not digital. It's analog because
Digital
it can
would be one like the.
on or off only. You know?
Right.
Yeah. I mean, the digital is on or off. You know,
Yeah.
a digital signal is going to look like that on a scope.
Right.
An analog signal is going to look like that. It can be anywhere in between there, up and down. See, like this is an analog wristwatch. Analog gauges on a car have got a needle. Digital gauges have just got the numbers.
I don't like it.
Yeah,
Like
the,
a digital dash.
yeah, the digital
I
dash.
don't like it.
All right, let's go down here now. So that is number 3 is true. An analog signal continuously and smoothly changes. That's what I was just talking about. So that is true. Automotive computers and control modules use analog signals converted from digital signals. Number 5 is false. Let me tell you what a computer does. If a computer sees an analog signal, the computer has got to change, it's got to convert the analog signal to a digital signal. In other words, it can't really use an analog signal, so what it has to do is, it has to decide what it's going to consider on and what it's going to consider off. And as this analog, if you do an overlay of this, in other words, let's say that it was going to say 2 volts was on, and let's say your signal is going to go higher than it. It's going to go, you know, but let's say your signal is going to consider, if that analog goes up, if it goes up that high, the computer is going to superimpose, dong. All right, now let's say it goes up here, and then it goes back down. The whole time it's up here, it's when it drops back below 2 volts, it goes, see, that's how it converts that. It's got, but whoever types that program or sets that circuit up has got to decide what's on and what's off. And you got a little digital analog to digital converters that have to be a part of the circuit. That's why a lot of our wheel speed sensors and also all of these position sensors, they're actually making little magnetic resonance, resistance element sensors in there so that they can make this signal that comes out of the sensor digital before it ever goes to the computer. We don't want to have to convert that dadgum signal because that's going to make it more expensive to build our computer, and this little sensor don't cost that much. It's a little old thing, but it can actually produce a digital signal. Remember on that Dodge Caravan, some of y'all saw that and some of you didn't. The Dodge Caravan that y'all were working on, and also this one Jimmy's got over here, and I can show you that when we get in to do a vehicle inspection on it. The wheel speed sensors on that one do not put out an analog signal. It puts out a digital signal. And if you know, nobody else knows this much, but if you take and go and back probe the 12 volt, it's got 12 volts in the ground going to it. All right, if you measure that with that sensor with a meter, you ain't gonna read a darn thing. It's gonna be wide open. You're gonna think it ain't no good. So with it plugged in, key turned on, 12 volts going, get a vapor clip and real gently go back probe it, because you got there's a little grommet up in there. You got to pop it out of the cabin and get it over and get to that connector. You gently back probe it. You're not damaging the connector. You're not going to damage the seal. You're going to hook your voltmeter to it, and this is with the key on and not the engine running. And you're going to hook to, you can actually measure to both sides of the sensor. And as you turn that wheel real slow, you'll see that voltage go up and down. And it's actually, I got it on a scope out there, and it coming out of that sensor, that signal is digital. It ain't moving a heck of a lot, but it's a digital signal. Now the computer's looking for amps. We're actually measuring volts, but both of them are there. And it's going to give you a square wave no matter, no matter which one you're measuring. Anyway, I got off on that too. But we were talking about analog and digital signals, but nowadays most of the sensors, if it's a Hall effect sensor, it's wanting to put out a digital signal. I'll tell you something else. On these, some of these Jeeps and some of these other ones, they have on the end of a new sensor, and some people have seen this, it comes with a little paper spacer stuck on it. And you're supposed to slide, and it's got an adjustable slot where it mounts. And whenever you slide that thing down so the paper spacer is against the little wheel, you just leave the paper spacer in there. And that paper spacer puts that so that if you looked at it, if you looked at a cross section of it like this right here, there'd be a paper spacer that's actually stuck on there. And it would skin off of there as soon as you spin it over. It just skins it off and it goes somewhere and it don't hurt nothing. But that's got your spacing perfectly for that sensor. And you'll buy one with a spacer. You can actually buy the little spacer by itself. so you can, so you're putting,
Reset it,
huh?
so you can reset it.
Yeah, so you can, when you're, like if you had the transmission out and you had to put it back in, and I'm gonna tell you something, whenever I was, just becoming introduced to these Hall effect sensors, I would shove the sensor as close as I could get to the wheel to get the most voltage, and that don't work, because when we would do that, it wouldn't run worth a crap. And then we get a little too far away and it wouldn't run, I mean, just adjusting it by ear with the engine running, you can't always get to it all that good. I found out that too far and too close, it's gotta be just right. And that's why I had that spacer on it. You see, boy, was I ever in for a surprise. Because on the old Jeeps, you just bump that thing in as close as you can get so you can get good, because they had that 480 millivolts to even read it. And closer would make it higher on the old analog sensor, but this one was different. And it was a free wire sensor. I sort of got off on a tangent there. The entire PC, yeah, the entire PCM must be replaced if a change in programming is needed and the PROM is not replaceable.
What's the PROM?
Programmable read-only memory.
That's true.
All right, now on your GMs, anybody that's ever replaced a computer on one of your older GM cars would know that you got a little centipede chip that you got to pull out of the old PCM and put in the new one. And you got to put it in there the right way. Yeah, whenever there's a little, it looks like a little, on a circuit board. One of these little black squares, it's got all them legs coming off. So all right, now we got, let's go here. The entire PCM has to be replaced if for change in programming is needed, a PROM not replaceable. A shift solenoid can be tested with a DVOM or by air testing. A shift solenoid can be tested with a digital voltmeter or by air testing. This is a digital voltmeter. Everybody seen one of these before?
We tested by that, but I don't know about no air test.
Well, I don't know. Think about your shift solenoid. What's it doing? Remember I told you about the shift solenoid stopping up a passage?
Oh, yeah.
All right. So you know what I used to do with a shift solenoid to test it? I would take that shift solenoid and it got a little port end of it. I would blow in it like that. And I had my little wires hooked up to the two wire terminals, and I would touch the power around, and it would go click. I mean, when I left it, moved it off, or went the other way, depending on any solenoid that's going to move air or fluid, you can actually test it by, you can put a hose on it if you don't want to put your mouth on it or whatever and blow through it while you're putting power to it. You can find out if it's working or not. And that's how that works. Jimmy Batchelor one time had a pickup truck that he pulled the transmission out of, a Ranger, somewhere that one over there, and it didn't have a second gear. And so he pulled it out and he looked at the valve body in there, and he found out, well, first he put the little shift solenoid in there, and it didn't fix anything, and then he went deeper in the valve that was behind the shift solenoid. He reached in there and he found a piece of cloth where somebody had, this is funny now, somehow or another when they had wiped the dipstick or something, that somehow a little piece of a shop rag got down in there, and I don't know how it got in there, because he hadn't been in that transmission before, and it stopped that shift valve from moving. And so when he took that little piece of hair, cloth out of there, he didn't even need to buy that $50 part. It was just a little bit, the tiniest little thing. So yeah, 7 is right. You can test it by air. But let me ask you this: if I test it with a DVOM, do I know that it's good for sure?
No, you need that.
What if the solenoid is stuck on? What if the my moving part on the inside of it is stuck? And you're going to see occasionally you're going to pull a code that says 2-3 shift solenoid performance fault. You ever seen it? You might see something like that on a GM car. They like to do that. That means there's nothing electrically wrong with the solenoid as far as the computer can tell. But I told it to do something, and whatever I told it to do didn't happen. Because I'm looking at my speed sensors. I know how fast the engine's turning. I know how fast the turbine shaft is turning. I know how fast the output shaft is turning. I know how fast these ought to be turning in third gear, and I didn't see third gear. Or I didn't see whatever I was telling this thing to do didn't happen, even though I don't see an electrical problem with it. So there's something going on down there. That's a performance fault. Is what it is. It's not electrically bad, but it's not performing, and that's what you need to look at there. Sometimes you'll look at these codes and say, "What the Sam Hill are they talking about?" All right, but that's what that means. Vehicle sensors produce an output signal that can either be analog or digital. And we talked about that already. That's number 8 is true. Number 9, OBD1 technology can diagnose and detect only system failures and system degradation. That's false. They've got, rationality checks and all kinds of stuff they do. Like your OBD1 systems, as they got a little more sophisticated, would know if it was telling the idle air control to open and it didn't see the mass airflow, it reflected there was more air coming in, it would throw you a code for that. You know, a 5 series code or something. So yeah, that's false. Serial data can be used when a no code condition occurs. That is true unless your network is down. On our Chevy Cobalt that we're fighting with out there, whenever the network goes down on that dadgum thing, now he ain't talking to no scan tool. It will tell you nothing. Your scan tool is just basically a boat weight in your hand. I mean, it's a nice piece of equipment, but if the network is down, the scan tool is useless. So the serial data is wonderful if you have serial data, but you may not have if you got some issue there. Number 11. This is a multiple guess. Okay, the blank stores the program control instructions for the powertrain control module. A, transmission control monitor. B, onboard diagnostic 2, which would be OBD2. C, programmable read-only memory chip. Or D, engine control unit.
I think it's C.
Yeah, that's C. That's what we were talking about earlier. To measure electrical values such as voltage, current, and resistance, the blank may be used.
A.
That's a DVOM, digital voltometer. What's a DSO?
Something like that.
Anybody know what a DSO is?
Digital signal oscilloscope.
Very close. Digital storage oscilloscope. They call it a digital storage oscilloscope because it can save the pattern and let you look at it later. The one that we had on the blue one that was the cathode ray tube screen, it couldn't save nothing. That's why I had to take my digital camera out and shoot a shot of it. So I basically was using my camera to make the digital storage part of it. The sensor that measures absolute pressure or vacuum in the intake manifold is the MAP sensor. Now sometimes you're going to see a vacuum sensor referenced or something like that. And you remember that vacuum and pressure, if you add them together, come up to barometric pressure for your prevailing area. If you've got 18 inches of vacuum and 12 pounds of pressure, you add those up and you're going to get manifold, whatever the barometric pressure is prevailing. We used to get, sometimes these guys would be fighting with a map sensor that wouldn't be reading its right. Be reading like a really crazy pressure. And the guy would say, man, I must have a bad map sensor. He'd go throw another map sensor on it, and they would read the same way. What's up with that? And I said, there's a hurricane coming. We got some pressure, air pressure deals going on here. You got to be paying attention to the barometer so you'll know, All right, but anyway, switches in an electronically controlled transmission or transaxle are controlled by what?
Hydraulic pressure.
The hydraulic pressure basically controls them, but they can be controlled also by mechanical linkage or manual operation, so all of the above is the right answer for that one. The diagnostic trouble code group designated by alpha code UO, U1, U2, and U3 is
Network code.
network code. That's what we're getting on there. Doggone Cobalt. And we got the transmission computer's bad on it. It's got power and it's got ground. It's got everything it needs, but it ain't talking and it ain't shifting. And we ain't got no speedometer operation.
So you got a crank?
Oh yeah, it's been running. It's been cranking that thing for a while. Questions or comments?